Okay guys, so what we're going to do today is we're going to continue talking about how we can describe what is happening on a graph by looking at it a little bit more in depth, okay? Yesterday, if you remember, we used the first derivative to find a variety of things, to find maxes or mins, to find out where the function's increasing or decreasing. And the one thing, and it's really something that you could probably get to on your own, like you could probably figure this out if you really thought about it and went through the process. This is what it should look like. But the one thing that the first derivative really doesn't tell us is how curvy the graph is at different times. And that's a really bad way to say it, but we haven't really talked about the vocabulary yet. Like, I know where this function's increasing or decreasing, but there's a bunch of different ways that I could draw that in this case. Whoops, and I drew that very poorly. But what we don't know yet is what the first derivative won't tell us is how much curvature there is to the graph. The curvature of the graph has a special name. It is what is known as concavity. Okay, now as you can see here, concavity is the rate, it's a measure of how fast or slow the function is increasing or decreasing. Another way to look at it is the rate at which the rate is changing. That is written correctly, the rate at which the rate of a function is changing. It's kind of hard to understand when you think about it analytically, what does that mean, the rate at which the rate's changing? But when you look at a graph, it's actually fairly easy to understand. Now, there are two different types of concavity that we can have. We have what is called concave up, and then we have what is called concave down. A graph that is concave up, like a really simple way to say it, a graph that is concave up kind of looks like a smiley face as we look at the graph. Okay, so if a graph is sort of smiling at you at any interval on the function, then we say that the function itself is concave up. Another way to look at this, and this is kind of how they use it on the AP tests sometimes, is if I were to draw a tangent line at any point along an interval that a function is concave up, then the tangent line itself would always be drawn below that function. Notice how both of those lines are located below, their y values are less than a graph that is concave up. Conversely, a graph that is concave down looks like a frowny face on any given interval. Or if we were to look at that in a different way, we could say if we were to draw a tangent line, that the tangent line would always appear above that function that we are talking about. So you can see here, everywhere on this picture that the graph is drawn in red, we have a graph that is, the portion of the graph is concave up. And anytime it's drawn in blue, we can say that it's concave down. And hopefully that kind of makes sense as far as what we're talking about here, concave up versus concave down. Now, you might be asking, okay, we talked about concavity, that's fine. What we're going to do is we're going to figure out how to determine where a function is concave up versus where it's concave down. Because I look at this and I can see just by looking at it that the colors change right there, but I'm not exactly sure where I changed from concave up to concave down at any of these different places. I can see the graph and I can tell basically where it's behaving like that, but we want to find out exactly where that is. Now, in order to do that, what we're going to use, you can see that here, is we are going to use the second derivative. So if I was looking at this function, x to the third plus 12x squared minus 1, I can tell you right now that that function is going to take on a basic shape like this. It's going to be concave down to start, and then it's going to be concave up after that. But to decide exactly where it changes from concave up to concave down, or concave down to concave up, what we're going to do, and some people struggle with this a little bit, is we are going to take the second derivative, because the second derivative actually tells us concavity, and we are going to use the second derivative in almost the exact same fashion that we did using the first derivative, okay? A couple things to note. If I take a value, any x value, and I plug that into the second derivative, and I get a positive number, that tells me that the second derivative will be concave up. So if I have 6x minus 24, and I take positive 5 and plug that in, 6 times 5 plus 24 gives me a positive number, which means at x equals 5, I can say that my original function is going to be concave up because I got a positive number. Conversely, if I take a negative number, or if I take an x value, I plug it into the second derivative, and I get a negative number, that tells me where the second derivative is going to be where the second derivative is, where the original function is going to be concave down. So if I was to look at the second derivative and set it equal to 0, just like with the first derivative, that is the only place where we can change from being concave up to concave down or vice versa. Those have a special name. They are what are known, where the second derivative is equal to 0, as a point of inflection. Now again, that is different from a critical point. A point of inflection is where the second derivative changes from a positive value to a negative value or vice versa, or if we look at it, it's where the original function changes from concave up to concave down or vice versa. So you can see on this point, on this graph right here, the definition of a point of inflection is where the second derivative changes from concave up to concave down, and we've got that labeled on this picture here. Okay, now, we know this already, so let's take a look at our function that we had. If I have my second derivative, my first derivative is 3x squared plus 24x, we could use that yesterday to tell where my original function's increasing and decreasing, or if I took the second derivative, I get 6x plus 24. Now, if I were to take that, and set it equal to 0, 6x plus 24, I set that equal to 0, when I do that, I get x equals negative 4. Now, negative 4 is our point of inflection. So I take my point of inflection and I put that on my number line. Then, just like what we did before, we take our values that are less than negative 4, some random value, negative 22, and I put that into my second derivative, and that will tell me whether or not my function is concave up or concave down at that point. And in this case, I get a negative number, so that means my original function is concave down. Then I do the exact same thing on the other side. I take a number larger than negative 4, like 0. I plug that in, and I get a positive number, which means my original function is concave up. So although originally we knew that my function, was concave down, and then it changed to concave up somewhere along the line, now I know that my function changes concavity at x equals negative 4. So it's a more specific definition of what is going on as far as where things are concave up and concave down. So just like with the first derivative, there are steps we can follow, and they're very, very similar. Step number 1, take the second derivative, set it equal to 0 to solve for the points of inflection. Step number 2, take those points of inflection and put them on a number line. And then step number 3, put points in on either side and then identify the type of concavity that we have on that interval. So if you're taking notes and you want to fill that out, take a second to write those down by pausing the video. And then once you're done, we'll move on and do one more example to make sure that we understand what's going on. So let's take a look at this function. If I wanted to find the points of inflection and everything else that's going on with this function, I would just say I need the second derivative. The second derivative here, or the first derivative, would be x to the third, not divided by 12, divided by 3, minus 3x squared minus 2, divided by 2, minus 4x plus 2. My second derivative here would then be x squared minus 3x minus 4. So what I'm going to do now is take that and set it equal to 0. I factor that down. I get x minus 4 times x plus 1, which means my points of inflection here are at positive 4 and negative 1. So now what I do is I go and I make my number line. Okay, I've got negative 1 on my number line. I got 4 on my number line. I choose a number smaller than negative 1, negative 22. Now again, just like with the first derivative, I can put this into any version of the second derivative I want. The one that makes the most sense to me would be the factored form. Because if I take negative 22 and plug it in, I get a negative number times a negative number, which gives me a positive number, which means my original function is concave up on the interval from negative infinity to negative 1. If I choose a number between negative 1 and 4, what happens is I get a negative number times a positive number. I chose 0. A negative times a positive gives me a negative number, which means my function is concave down from negative 1 to positive 4. Then I choose a number bigger than 4, like 90210 sounds great. So I got 90210. And I do that, and I get a positive number times a positive number, which gives me a positive number. So I can say that my original function is concave up. So if I was asked, I could say it's concave up from negative infinity to negative 1, and from 4 to infinity. And then we can say that it's concave down from negative 1 to positive 4. Notice the only thing that people really struggle with when it comes to this is you look at it and you're like, oh, this seems like the exact same thing we did with the first derivative, because it is the exact same thing that we did with the first derivative. The difference is we are evaluating all of these things using the second derivative instead, which means it's telling us something different about the original function, even though the process is exactly the same. So if you have any questions about this, please come on in and ask. If you need to know anything about the difference between these two, please let me know. Otherwise, hopefully that all made sense.